Okay, this video is about some notes that we are taking on half-life. So we're on page 29. You probably already have drawn in some graphs, and we did a lab last time and we figured out that the pattern of radioactive decay, or the pattern of half-life, is an exponential decreasing pattern. So we wrote down a bunch of patterns and we found out that this one is the one that matches half-life. So we're going to talk about how to solve some problems with half-life. So first of all, you're going to be able to look at a graph and figure out the half-life, and you're going to be able to use half-life to figure out how much of something is left after it's decayed for a certain amount of time. So these notes are pretty short. Let's start by writing down a definition for half-life. We wrote this down before, but I just want to review it with you. Half-life is the amount of time, so it is a time, that it takes for half of a sample of radioactive atoms to decay. And again, just a reminder, when I say decay, that means turn into a different element. That doesn't mean like disintegrate into nothingness. So let's imagine that I have a half-life of 5 minutes. If I start with 100 atoms and they have a half-life of 5 minutes, after 5 minutes, 50 of those will still be radioactive and will still be that same element. After another 5 minutes, 25 of those same elements will be left. And after another 5 minutes, only 12.5 will be left. So the amount of atoms that are still radioactive, that are still that same radioactive isotope, keeps decreasing by half. Okay? Now, one thing that you need to know about half-life is that we cannot change it. So you guys know that nuclear waste storage and disposal is an issue that we have to deal with. And it's an issue especially because some of the things that we're trying to store have really, really long half-lives, like billions of years. So it would be nice if we could like speed that up and get them to decay faster, but we actually cannot change the half-life. We can't heat things up to change the half-life. We can't add pressure. None of those things affect the half-life. So you need to know that temperature, pressure, and concentration do not change the half-life. Okay, so now I'm going to show you 2 examples of problems you need to be able to solve. So one of them is you need to be able to look at a graph like this one and figure out the half-life. So this is, on the x-axis we have time. On the y-axis we have activity counts per second. You can think of this as like how much radioactivity there is. So we start out with 80. Sometimes this is like number of radioactive atoms. Sometimes this is grams of radioactive substance. Either way, it's the same. We start out with 80. The half-life is the time it takes for this to cut in half. So half of 80 is 40. 40 is right there. The half-life is the time it takes us to get from 80 to 40. So it's this time on the x-axis right here, which is 6 days. And what's nice is the half-life is the same all the way through. So the time to go from 40 to half of 40, which is 20, is also 6 days, right? And then 20 to 10 is also 6 days, and 10 to 5 is also 6 days. So you can see the half-life is 6 days all the way through. So you need to be able to look at a graph, figure out the half-life. That's pretty easy. Then we're going to do one other kind of math type example that we're going to write down in the notes, and this is the last thing we're going to write down, just this example and how to solve it. So if there are 60 grams of Np240, that's neptunium. It's an element you probably haven't ever heard of. If there's 60 grams of that present, how much Np240 will remain after 4 hours? hours. And then I'll tell you NP240 has a half-life of 1 hour. All right, so what we need to do is make a kind of a data table with time and amount. And for any type of problem like this, you should set up this table. I'm going to do it right here since there's a natural line here that I can use for my table. So on the left, I'm going to do time, and on the right, I'm going to do amount. Now, whenever you're solving these problems, every single time, you're going to start at time 0. So that's basically saying no time has passed, this is the beginning. So time 0 is the beginning. At the beginning, I have 60 grams. Like, that's how much I start with. So we're going to start with 60 grams over here. Our amount is in grams. Our time is in hours. Okay, the half-life is 1 hour. So after 1 hour, I will only have half of this still as Neptunium-240. So that's 30 grams. The next half-life would be 2 hours. So that would be 15 grams. And then 3 hours is going to be 7.5 grams. And then after 4 hours, I'm only going to have 3.75 grams of NP240 left. So that is my answer. All right, so for all of the half-life problems, you set up a table like this. Now, the half-life won't always be 1. If your half-life was 5 days, then you'd be counting by 5. So you'd be like 5, 10, 15, 20. Make sure that you don't double the time. You count by the half-life. So if it's 7, you're going to go 7, 14, 21, 28. If it's 2,000, you're going to go 2,000, 4,000, 6,000, 8,000. Don't double this side. Count by the half-life. This side, you cut in half. So that's how you do those problems. Let me know if you have any questions.